Not sure whether people have a hard time to get up early. We'll see.
I don't know about Harvard, but by MIT time, we're still 5 minutes away from the beginning of the seminar, I guess.
Oh, I see. You mean people start 5 minutes late after?
Yeah, pretty much for everything. Yeah.
I see. Do you know how long will be your talk? Like we have 90 minutes, but you can take whatever time.
It's probably shorter than 90 minutes. I was planning for closer to 60 to 70 minutes.
Okay.
Yeah, but if there are questions that come up, then yeah, it can get arbitrarily long, I guess.
By the way, also will you also have time for both for the lunch time and dinner time?
Yeah, I should be free.
Okay, so I will ask people and ask them send me an email, and we'll gather the time which might be the best, and then meet somewhere at Harvard Square.
Sure, yeah. Harvard Square is probably extremely busy these last couple of days, given all the new students that arrived. I was there a couple of days ago, and there was a huge fight for a blue bike near the
I see.
station.
I see. So maybe we can gradually start, I think. Let me do the recording as well.
Okay. Seems
okay. So welcome everyone. Welcome back to Harvard CMSA Quantum Matter in Math and Physics seminar. First, apologize that we slightly shift forward the meeting time because there are some conflict with other Harvard faculty, the course they are teaching. So we shift to the 9 a.m. to 10:30, and if there are more people have a problem, then we will see how it goes. But we start with 9 a.m. just by default so far. And this term we have a Monday and Wednesday quantum matter seminar. Either of them, one of them will be quantum matter in math physics, as the previous semesters and previous years goes. But there's also another one called topological quantum matter, run by Jie Wang, a new Harvard CMSA researcher postdoc. And I also like to mention that this term we would like to have some after presentation, after seminar gathering, like having a meal together somewhere at Harvard Square. And most of the speakers might still be present on Zoom, but if people have interest to join the lunch or dinner, it really depends on the opinion from gathering from the feedback from the people, then please send me an email. So if you have interest to join a meal together today with Zhengyan, then please send me an email better by 11:30 or so, 11, and we'll decide whether we go for lunch or go for dinner. Okay, so today we are very happy and honored to have Zhengyan Darius Shi from MIT. He'll be speaking about his recent work on gifts from anomalies, new results on quantum critical transpose in non-Fermi liquids. Let me remind the audience, please feel free to interact with Zhengyan and ask questions. So we welcome Zhengyan to speak. It's yours. Take over. Thank you.
Yeah, thanks, Juven, for the invitation and the introduction. Yeah, and just wanted to repeat what you said. Please feel free to interrupt at any time. The more questions, the better. So yeah, the topic today is gifts from anomalies, right? And we want to present some new results that we have on quantum critical transport in a class of non-Fermi liquid metals. And this work is based on 2 papers that we put out on arXiv, one in April, one in August. And the main focus of today's talk will actually be on the paper on August, from August. And before we begin, let me introduce my wonderful collaborators. So Hart Goldman is a postdoc at MIT. Dominic was a postdoc at MIT and is now a professor at Perimeter. And of course, my advisor is Sento, whom you all know. So yeah, so now let's dive in. So before going to non-Fermi liquids, let me just give a one-slide summary of what we know as the standard model of metallic systems, namely the famous Landau Fermi liquid theory. So I think it's really hard to overstate the importance of theory, this Fermi liquid theory, and the universality of its applications to generic systems of interacting electrons at finite density. Right. So some of the hallmark features of Fermi liquid theory includes stable coherent quasiparticles with a very small scattering rate, which scales as t squared. Right. As the temperature gets low, the scattering rate becomes much smaller than the characteristic energies of the individual quasiparticles. And this leads to really many, many universal thermodynamic and dynamical properties of the system. So for the purpose of this talk, we'll focus on the one particular dynamical signature, which is the DC transport. So in the presence of small disorder, the DC transport in a Fermi liquid will generically take the form where you have a constant term and then a term proportional to t squared. Right. So this t squared resistivity has been measured in numerous materials and confirmed beautifully. However, we know from the last couple of decades of experiments that Fermi liquid is not the whole story, right? There are a wide range of materials for which we've seen a very clear demonstration of deviation from Fermi liquid predictions. So one of the most famous examples of such experimental signatures is a robust T-linear resistivity over a wide temperature range in sort of a growing list of materials. Right? This includes the early examples of cuprate high temperature superconductors, and then started to sort of branch out and include heavy fermions, and even more recently twisted bilayer graphene systems. So here I just show you sort of 2 very representative plots for this T-linear resistivity. On the right-hand side, we have a heavy fermion metal, which is ytterbium dirodium disilicide. And on the left-hand side is a selection of cuprate materials. This is from a experimental synthesis by Legros et al. From 2019. And you can see that this robust T-linear resistivity is really sort of extends over many decades in temperature, and it seems to be very sharply distinct from the prediction of Fermi liquid theory. Nevertheless, from spectroscopy, we can still see that the Fermi surface in these systems seem to be robust. Now, but the presence of a T-linear resistivity tells us that there is no Landau quasi-particle description. So this wealth of experimental evidence suggests to us that we really need to look beyond Landau Fermi liquid theory in our search for theoretical models. So the other ingredient that I mentioned in the talk, in addition to non-Fermi liquid, is quantum criticality. So where does quantum criticality come in these materials? So again, our motivation will come from some experiments. So it turns out that in many of these experimental systems that have T-linear resistivity, they're very close to some putative quantum critical points associated with Landau ordering transitions. So here I draw a sketch of such a generic phase diagram of this type, right? As you tune some parameter at zero temperature, so this parameter is denoted as R here, you can go from a disordered paramagnetic metal to some kind of ordered state. So in the particular example of this heavy fermion metal, we have a anti-ferromagnetic ordering on the left-hand side. And then in between, so when you tune between the ordered state and disordered states, there's a quantum critical point in the middle and its associated quantum critical fan. So what's remarkable is that if you go to the experiment and you try to fit the resistivity at different points in this parameter space as a function of temperature, you find that there's this orange region, right, where the resistivity is robustly T-linear, and this orange region seems to coincide with the quantum critical fan that's associated with the ordering transition. This gives us our first hint that somehow, there's a possibility that the strange metallic behavior in these systems is very intimately connected with quantum criticality. And in addition to this, there's a more direct and perhaps more appealing evidence, which is that if you look at the conductivity as both a function of frequency and temperature, you see that the conductivity is not just any frequency, it's not just a general function of omega and t, but rather it's some power of t times a scaling function that only depends on the ratio omega over t. So this is telling you that the only energy scale of the system at finite temperature is just the temperature. So there's all the other intrinsic microscopic scales have been washed out, and you're really left with quantum critical scale. So again, the evidence here from experiments is, I would say, less convincing than the robust T-linear resistivity, partly because it hasn't been measured in as many materials. And here I showed one of the earlier measurements from the cuprates, the bismuth 2212. And here you see from the plots that there's reasonably good scaling over some small range of omega over t, roughly extending from 0.5 to 1.5, right? But you can argue that the curves look kind of noisy and it seems to diverge for larger values of omega over t. But really, I think the most clear and convincing example of such scaling is again in the heavy fermion example that we saw on the previous slide. Right? In a recent experiment from Prochaska et al. From 2020, they plotted the resistivity, plotted the conductivity, multiplied it by some power of t, and they found a beautiful scaling curve, right, extending over a range of temperature. And also the range in omega t here is much larger, right? It starts with a very, very small number, you can see from the very left hand of the plot, and extends all the way to 10 times, 20 times, it extends up to 10 or order 10 to 20. And you find that, if you try to do the scaling collapse fit, then the best fit parameter is exactly alpha equals 1, which is again consistent with this T-linear resistivity that we observed in DC. So putting all these pieces of evidence together, right, we have quantum criticality and we have non-Fermi liquidness. So it's very tantalizing, right, for us to find a minimal model in which both of these ingredients play a role. And together they generate some kind of conductivity signal that would be beyond this description of Fermi liquid theory. So this brings us to the central question in this talk. Can we find a non-Fermi liquid metal that displays any quantum critical conductivity at all in the infrared limit? So we emphasize that at this stage, we're not yet going to try to match two experiments or try to reproduce the T-linear resistivity, but rather we're just trying to do some model searching and see if theoretically these two ingredients can be put together and yield interesting results. Okay, so in order to sort of be more concrete, right, we need to specify the particular paradigm, right, the particular set of models that we work with. And these models will be chosen from what's called the Hertz-Millis paradigm, which can be viewed as the minimal model for such non-Fermi liquids. So by minimal, I just mean it's the simplest thing you can do to destroy a Fermi liquid while preserving its Fermi surface. And how do you do that? Well, we just take a Fermi liquid and then we couple it to some critically fluctuating Landau order parameter. And this was an idea that has been around since the early days of Hertz and Millis's work, but has been developed by many others. And the basic action, right, I'll draw it in picture here and make it more concrete later. But you have the Fermi liquid, which is on the left. And then you have the Landau action for the boson. For, here we only kept the quadratic terms. You can, in principle, keep higher order terms. And in this Landau action, the action that you're usually familiar with from statistical field theory will be where the kinetic term is proportional to q squared. And that would correspond to taking a value of z, which is equal to 3. However, in some natural contexts where this kind of model shows up, for example, in the nu equals 1/2 composite Fermi liquid state of quantum Hall, we see that z can actually be 2, right? So given the existence of these interesting examples, we'll leave z to be arbitrary here, okay? And generally, we should think that z is between 2 and 3. And many of the results will actually hold for arbitrary values of z, so it doesn't matter what z we pick at this level. And then, okay, so we have the, yeah, Juven?
Oh, yes, question, just make sure I follow the central question. If I can, if you want to complete this slide, you can, but I just want to ask something about central question.
Yes, I can go back.
The emphasis here is the infrared limit is the difficulty here, or?
Yeah, so when we talk about quantum critical conductivity, right, we're talking about conductivity associated with some IR fixed point, which is scale invariant. So that's, yeah, so these two difficulties sort of come hand in hand, right? If you want to have a quantum critical conductivity, you have to go into the deep IR limit. And that's something that's difficult to do within the current theoretical framework.
So what has been done in the past and still make this problem difficult? Can you just like
Yeah, so I'll have a discussion of that after I introduce the models. So it's I think it'll be easier to talk about why it's difficult after we know what the Hertz-Millis model is. Yes.
Okay.
Is that okay?
Sure.
Yeah, thanks.
How about just change to Fermi liquid? What will be the statement here for the Fermi liquid? Like in comparison.
Yeah. Oh, so for Fermi liquid, if you really want to talk about the clean sort of IR fixed point of Fermi liquid, right? Then in the infrared, there is just no quantum critical conductivity, right? The conductivity is just some Judah peak with a Judah weight, which is determined by the densities, etc. Right? Yeah. So now we want to do something more, right? We want to say that the existence of quantum critical fluctuations in these models can possibly give rise to a conductivity that's not just Judah peak.
And when you say, can we find such a non-Fermi liquid, what do you want to find in the end? Is a theory, or it's a model, a field theory? It's a...
Yeah, we just want to, well, at this point, we should be open to all kinds of possibilities, but we just want to find a model, right? Currently, there is no model for which we can find critical conductivity deep in the IR limit, right? So we want to see if there exists a model, and if so, can we do any controlled calculations in this model?
Thanks.
Yeah, that's the central question. Okay, so yeah, coming back to the Hertz-Millis paradigm, I told you about, we have the Fermi liquid and we have the Landau action for the boson with general value of Z. And then we just have some interaction between the bosons and the fermions, right? So in the RG sense, the most relevant interactions that we'll include will be where a boson comes in and excites a particle-hole pair. And in the process, it carries some form factor Fk of Fkq. And this Fkq really tells us, right, what's the order parameter that's being broken across the phase transition, right? Because phi couples to this order parameter. So in general, we'll consider two broad classes of interaction form factors. One class will be inversion even, right? So as you can see, when you flip the momentum of the fermions, the inversion even order parameter will be invariant. So one important class of examples will be isonematic quantum critical points. So this has been discussed extensively in the context of, in the context of many different materials. And the second class will be inversion-odd order parameters, which where the form factor is odd when you flip the momentum k. So an example of this would be a transverse U1 gauge field, right? This appears in the context of the nu equals 1/2 state. And also for cases that are not U1 gauge field, we'll give them a general name, right? Motivated by the original sort of proposals by Chandra Varma in the context of cuprates. Then we call them loop currents, right? They have the symmetry, this inversion odd property justifies why we call it a current. But really, we just want to think about the general case, right? Many of our transport results in the end will turn out not to depend on the specific form of this f function, but rather depend only on the inversion symmetry properties. So given the statement of the model, right, we want to understand some general IR singularities that are present, right, to understand the structure of the IR fixed point. So to do that, we go back to the action. We go back to the Landau action for the boson. And we notice that if we integrate out the boson in favor of the fermions, then we generate some effective interaction for the fermions that's long-ranged. And when this interaction is long-ranged, the fermionic quasi-particles associated with the original sort of non-interacting Fermi liquid state is in fact destroyed. And how do we see that? We see that in two steps, right? If you just do a simple-minded one-loop calculation, right, then at some energy scale, the boson scattering off of these particle-hole pairs will generate a self-energy, right? So the boson self-energy will turn out to be proportional to omega over q at small omega and q. So if we combine this boson self-energy, so first of all, notice that this boson self-energy will dominate over the barokinetic term, this lambda omega square in the IR limit. So then the remaining terms in the boson quadratic action will just be the q to the z minus 1 and the self-energy omega over q. So if we compare these two terms, we find that the boson the critical fluctuations of the boson will have a dynamical exponent, which is equal to z. So in the standard case where z equals 3, right, this recovers the familiar story of Hertz-Millis criticality. And at an even lower energy scale, right, the first effect, the Landau damping of the bosons that we discussed, feeds back onto the fermionic sector. And what it does is that it creates a fermion self-energy, which scales as omega to the 2 over z. So you see that when z is between 2 and 3, this fermion self-energy is much, much larger than the energy, which is omega, which means that this is in sharp contrast to Fermi liquid behavior, right, where the self-energy goes as omega squared. So the fact that the self-energy goes as omega to the 2 over z tells us that for general values of z between 2 and 3, the fermionic quasi-particles have been destroyed, and we should expect a non-Fermi liquid state deep in the IR. So this comes to Juven's point, right? It seems like we understand the IR singularities, but remember, this is just a one-loop calculation, okay? However, there's been no shortage of perturbative attempts to control the theory, right? To introduce some kind of either large n or small z-2 expansion. Over the years, I'm flashing a slide here, which gives you a brief overview of the landscape of expansions that people have come up with to try to tame the IR fixed point. And I won't have time to go into the details, but the general conclusions from these perturbative expansions is that the IR singularities of the one loop results are largely preserved. Right? There might be small anomalous dimensions that show up at some higher loop order. However, the basic conclusion that this is a non-Fermi liquid seems to be robust in the sense that the quasi-particle self-energy for the fermions always seems to dominate over the bare energy. So these perturbative expansions are very helpful, right, for us to have some faith in the one loop results in the general structure of IR singularities. But it turns out that to understand transport in these theories remains a difficult problem. Even so, because transport is really in a different dynamical regime as the quantum critical fluctuations, right? Transport lives at Q equals 0, where the critical fluctuations live at omega much less than Q. So this problem is what motivated us to consider alternative techniques to really study transport at the IR fixed point, to go beyond perturbation theory and see what we can say, even without all these complicated loop expansions. And this brings us to the central philosophy of this work, which is that we will take advantage of symmetries and anomalies, which are non-perturbative properties of the system that can be used to constrain various correlation functions. So as a brief reminder, so what are anomalies? Anomalies are exact quantum deformations of conservation laws. In the language of quantum field theory, these are deformations of the Ward identities satisfied by the Noether currents in your theory. So this is a kinematic property. It's not a dynamic property. So it has been considered in many applications to topological phases in the past decade. But it's sort of less, I think it's less appreciated in the context of strongly correlated electrons. So part of the philosophy of this work is to show that anomalies can be fruitfully applied even to the strongly correlated electron problem, and especially to optical transport. And the strategy, right, after we introduce our models later, we'll see that our strategy is to use these symmetries and anomalies, these non-perturbative properties, to derive as many exact results as possible. And then, if necessary, we'll augment these exact results with controlled expansions that we mentioned on the previous slide to go further. Okay, so any questions about this, our philosophy and the strategy? Okay, if not, let me just move on. And you will really see that the distinct anomaly structures of different models will determine the ultimate conductivity scaling at the IR fixed point, which is a central conclusion of our paper. Okay, so to talk about optical conductivity, I have to talk about two different contributions. This classification, sometimes the terminology is confusing, so I think it's good to introduce it in the beginning, where we talk about the coherent and the incoherent part of the conductivity separately. So to do that, we go to the IR fixed point theory, right? And we split the space of operators into the conserved subspace and its complement. So if you have a split of your space of operators, then your current operator, which of course lives in the same space, can be decomposed, right, into a component along the conserved subspace and a component in the complement. And your current operator can be written as a sum of these two components. So the conserved part, we call the coherent part, and the non-conserved part, we call the incoherent part. So again, I remind you that this is in the IR fixed point theory with in a clean limit. And from the Kubo formula, we know that conductivity is related to a two-point function of the current. And because these two sectors do not mix, right, we can really decompose the conductivity also into a coherent contribution and an incoherent contribution. So generally, if there are any conserved quantities that overlap with the current operator in the IR limit, we expect the coherent part to be some Judah peak, right? And the incoherent part can be the quantum critical contribution that we're after. So now let's introduce our two different classes of models and see how these two different contributions come in for these models. The first class of models is what I call standard n equals 1 model. So this is really the model that people have been trying to study in the Hertz-Millis context for many years. Here, the interaction is just a single boson coupled to a single flavor of fermions, a single flavor of fermion. And this is exactly the Yukawa type interaction that I drew on the previous slide. So for this class of models, we can show using nonperturbative arguments that the coherent conductivity is exactly a Judah peak, as we expect. But for inversion even and inversion odd, the Judah peak can be very different. In particular, in the inversion even case, the interaction doesn't affect the free fermion Judah weight, whereas in the inversion odd case, the Judah weight is generically reduced. But a more interesting result that I want to emphasize is that the incoherent conductivity is exactly zero at the clean IR fixed point. So this tells us that critical fluctuations, although in principle they could do something, they actually don't do anything at the IR fixed point, at least as far as transport is concerned. So the same result applies to a number of perturbative expansions that I mentioned on the previous slide. But importantly, it doesn't apply to the random flavor expansion, which will be the second class of models that we consider. So in the random flavor expansion, instead of having a single flavor of fermion and a single flavor of boson, we enlarged our Hilbert space, right? So now we have n flavors of fermions and n flavors of bosons, labeled by these capital indices I, J, K. And the coupling between the fermions and bosons is still of the Yukawa type, but now the Yukawa coupling itself is a random coupling. So this GIJK set of independent Gaussian complex random numbers. And yeah, you can show that this has a sensible large n limit. So here, if we look at large n, what we find is that the coherent conductivity retains the features that we saw in the n equals 1 model. Right? In fact, up to a factor of n, we get exactly the same set of results. However, for the incoherent conductivity, now the fluctuations from phi are indeed able to generate a non-trivial frequency-dependent conductivity, at least in the inversion-odd case. In the inversion-even case, turns out for symmetry reasons, it will still be zero. But in the inversion-odd case, we get a zero temperature fixed point conductivity, which scales as omega to the minus 2 over z. So we emphasize that this is a fixed point result because irrelevant operators can lead to corrections to this scaling, which will be outside the scope of this particular work.
Question?
Yeah.
Actually, I don't know what conserved sector means.
Oh, so by conserved sector, I just mean if you look at these operators at zero momentum, right? For example, let's look at the current operator at zero momentum. It's generally going to overlap with a number of other operators, right? And some operators will be conserved. For example, the total momentum of the system. If you think about a microscopic system, often the total momentum is conserved. And by conserved, it just means that ddt of that operator is equal to 0. So in the presence of such a conserved quantity, if the current overlaps with the momentum, you will have a Judah peak in the conductivity, which means the current doesn't decay even at infinite time after you apply a pulse of electric field.
I see. So here by conserved quantity, do you mean exactly conserved, or it can just be emergent?
I guess it can be emergent. Yeah, it can be emergent.
Mm-hmm.
Yeah, in the IR fixed point theory. Yeah, so it's an exact conserved quantity in the IR fixed point theory, but it's emergent from the UV sense.
Okay, thanks.
Yeah.
Oh, I have as well a question. It seems like at the Judah point, like literally, our non-Fermi liquid kind of turns from one like substance to another. Like in one case, it behaves like fermionic, and at the other one, like more bosonic. Am I right?
So are you thinking about the fact that the critical boson generates a conductivity? Is that what you mean by it turns into both a fermionic turns into boson?
Bosonic. Yeah. I just mean like it turns in some kind of electronic condensate, like what we see in superconductors, I guess. I meant this.
Well, so here we're not in the superconducting state anyways, right? So here, the point really is that the current operator, right, although it's built out of fermions, the current operator itself has bosonic statistics, right? So so in principle, right, the current operator can mix in the IR scaling theory, it can mix with other scaling fields. And it turns out in this theory, phi is such a scaling field which mixes with the current. And that's why you get these two contributions to the conductivity.
Oh, I see. Thank you.
Yeah, thanks.
I don't know if this helps or not, but for the most part, the types of models that are being discussed in this talk are coarse-minded transitions, which are not superconducting transitions. There might be some superconducting instability if you include pairing, but for example, the generic problem that people often study is like a Pomeranchuk instability. So the quantum critical point would be some kind of pneumatic quantum critical point in that case. But it's not, the transition itself is not a superconducting transition.
Yeah, thanks, Hart. Yeah, we'll stay in the normal state for now. Any other questions about the results? All right. So now I've given you the results. Let's actually go on and try to derive them. And this brings us to the roadmap. So to begin, we'll introduce the Hertz-Millis model, the Hertz-Millis action in sort of more concrete mathematical language. And we'll talk about the symmetries and anomalies that I advertised on the previous slide. And given these general statements about symmetries and anomalies, I will derive some exact results for the n=1 model. Right, this part will be a relatively brief review. Right, for the details will be included in our first paper from April. And then in the third part, we will go to the main focus, which is our optical transport in the random flavor larger model. Along the way, we'll introduce a technical tool that we develop called anomaly-assisted larger expansion. So this will really allow us to go beyond the standard larger expansion and obtain some non-perturbative results. And finally, after section 3, we'll go to some conceptual takeaway and future outlook. Okay, so the Hertz-Millis action that I wrote down earlier, right? I sort of presented you the action in picture. So now let's just review it in equation form. We have the fermion action, which just describes a free fermion with some dispersion epsilon k. And then we have the boson, which has this Landau action, which you've seen. And then there's these interaction terms. I mentioned that I call this the UV action, although it's not supposed to be the microscopic model of any specific system, but this is our UV starting point. Now we have to introduce what we call the mid-IR formulation, right, which is at a lower energy scale. So why do we do that? So in the mid-IR action, there's one crucial piece of physics that has been understood and preserved by all sorts of perturbative expansions, which is that the critical boson, right, in every patch can only mediate small angle scattering. So what's the physical reason for that? Right? If I take a fermion on the Fermi surface, say for example in this near the patch theta that I drew, and I try to scatter it by a boson with some momentum q. If the boson momentum is perpendicular to the Fermi surface, then it takes the fermion away from the Fermi surface, and there's a larger energy cost. However, the same boson, if it scatters along the parallel direction, so long as the momentum is small, the fermion actually stays very, very close to the Fermi surface. And this scattering is energetically favorable to the scattering perpendicular to the Fermi surface. What this means is that for any given small momentum of the boson, it only really couples to two small patches that are antipodal on the Fermi surface. So this is what people sometimes call dynamical patch decoupling, right? And because of this, if we want to flow to the right IR fixed point, it is desirable to focus on these, to zoom in onto these small angle scattering processes. And that's why we construct this mid-IR theory, which sometimes is also called patch theory. So what we concretely do is we divide the Fermi surface into a large number of patches, right? Where each patch has basically within each patch you allow the boson to scatter the fermion by some small angle, but you don't allow the boson to induce hopping of the fermion from one patch to another. And we'll label the width of the patch in momentum space as lambda of theta, and this lambda of theta will play an important role in the arguments later on. So how does the patch action, right? How does the mid-IR theory differ from the UV action that we wrote down. So on the fermionic level, instead of having the fermion dispersion over the entire Fermi surface, we'll then write it as a sum of the fermion action over different patches. So within each patch, right, we only include the dispersion, the linear order in the direction perpendicular to the Fermi surface, and we include a dispersion to quadratic order in the direction parallel to the Fermi surface. So it turns out if you do these one loop calculations, then you will see that you need to include both of these terms to reproduce the IR singularities that I mentioned earlier. So you can build a consistent renormalization group scheme based on sort of treating these two terms on equal footing. And you will see that in this renormalization scheme, there's some irrelevant operators in the UV theory that can be dropped. So one class of irrelevant operators would be additional curvature terms in dispersion, right? So here we're expanding around this particular patch, but we can imagine including higher order gradients, and these will not affect the critical behavior. And we can also include higher gradients in the boson fields or higher powers of the boson fields, which correspond to some self-interactions. And these will also be irrelevant under this RG scheme. And finally, we'll drop what we call the momentum dependence of the form factor within each patch. So notice that in the interacting part of the action, for each patch, we've basically specified a single number for the form factor f of theta. So of course, this f of theta will vary as we go along the Fermi surface, as we vary the patch index theta. But within each patch, it will not depend on the momentum. So this is a standard assumption that's made in the patch theory treatments of these problems. And it captures all the critical singularities. And we think that the additional momentum dependence will come as an irrelevant correction. So this is what we mean by the mid-IR theory. As you can see, this is not yet at the IR fixed point, right? The ultimate IR fixed point might not even have a clean-looking action. However, we'll park ourselves here for the following reason, which is that in the mid-IR theory...
Darius, I have a question on that last slide.
Yes.
I hope you can hear me. In this cartoon, it looks like phi is coupling different theta, but then I look at S int and it looks like they're at the same theta. So how literally should I interpret the cartoon?
Oh, yeah. So yeah, great. I should have probably explained that point. So you see in the interacting part of the action, phi doesn't carry a theta index, right? Phi is just still the bosonic field, but there is a sum over theta. So in particular, you can have a process in which this psi dagger theta, psi theta comes in, right? It interacts with some phi, but then this phi then sort of, on the other side of the diagram, you then have psi dagger theta prime, psi theta prime. So that's what I mean by the red line here. Yeah, so the boson can still mediate these interactions between the fermions. It just cannot hop a fermion from one patch to another.
Yeah, perfect. Thank you so much.
Great, thanks. Yeah, that's an important point. Yeah, so the advantage of the mid-IR theory that we'll see is that the non-perturbative anomalies, symmetries and anomalies will be very apparent from the mid-IR theory, although they're not at all clear how to see them from the UV theory. And the good thing about having non-perturbative symmetries and anomalies is that the constraints that we derive on correlation functions will just be exact all the way down to the IR fixed point. So we don't have to worry about further changes in the structure of the theory if we can derive exact results already in the mid-IR theory. We emphasize that we do not claim that these anomalies will be able to determine the full structure of IR singularities. For example, we're not saying that we can figure out all the anomalous dimensions for the fermions and the bosons. All we're saying is that the transport results we derive will survive. Okay, so now let's be more specific about the symmetries and anomalies of the theory by zooming into a particular patch. So in a particular patch theta, as I mentioned, the fermion action will contain the linear order dispersion perpendicular to the Fermi surface and the quadratic order parallel dispersion. And here I just call them K perp and K parallel. And you notice from this action that there's a symmetry which rotates the fermionic fields. And in fact, the symmetry, if you look at the entire action by summing over patches, it can be an independent rotation of the fermion field at individual patches. So we call this large symmetry group the U1 patch symmetry. And associated with the symmetry are some densities and currents, which you can figure out just by running the standard Noether procedure. And yeah, so I just write down the densities and the currents here. But now we notice, because the dispersion perpendicular to the Fermi surface is chiral in nature, that there is an anomalous current flow once we apply an external electric field to the system. So this should be familiar from the 1+1D chiral anomaly, right? Where if I just start with a chiral fermion and I drive it with some current, then non-perturbatively I will have a current flow, which is not corrected by interactions, or it's just not corrected by interactions. So this was important for in the 1D context for bosonization. And here we'll see that it will be similarly important in 2+1 dimensions. And the basic reason is that, before I go to our model, I'll mention that here I'm talking about the 1+1D example, right? But within the Fermi surface patch, technically it's still a 2+1D theory. But from the perspective of the anomaly, the parallel direction, right, or the direction along the patch, will simply be a spectator in the anomaly equation. You can roughly think about it as a bundle of 1+1D chiral fermions, whereas the number of bundles is proportional to lambda theta, which is the width of the patch. So it's of course not true. It's not true to think about this as a patch of 1+1D chiral fermions dynamically, but for the purpose of anomalies, you can think about it this way. And we have a more rigorous derivation from the Fujikawa procedure, where you can apply to this U1 patch symmetry. And you see exactly how this violation of current conservation can be derived in that context. Okay, so at this point, we've only talked about turning on an external gauge field and looking at the response of the system, and we've seen this anomalous current conservation. But the remarkable thing in this family of models is that the internal interaction between the fermion and the bosons resembles coupling the fermions to a gauge field. So if we just compare these two actions, right, on the top we have the interaction, and on the bottom we have the coupling of the fermion to an external gauge field. And we see that they're exactly equivalent to each other if we identify some there's some prefactor multiplying phi a as the gauge field that appears. So given that there's this exact equivalence, and given that the anomaly is really only a kinematic property, right? It doesn't depend on the dynamics of the boson. As long as I have this kind of coupling, I will have the exact same anomaly. I can just copy paste the anomaly that I had on the previous page, make the identification with the boson field, and we arrive at the anomaly equation for the interacting non-Fermi liquid Hertz-Millis model that we have in the absence of an external field, in the absence of an external vector potential. So this is the key statement that will be used over and over again. So I just want to pause and see if people have questions. Okay, if not, let's move on and consider the anomaly equation at zero momentum. Okay, so at zero momentum, if we do a Fourier transform of the above equation, we see that the gradient term, right, the divergence of the spatial current will just vanish, and both sides of the anomaly equation will involve some time derivative. And so if we move one term from the right to the left, we find that there is a new conserved quantity that has appeared, right? Although the original n thetas, the chiral charge densities, are not conserved, we find there's a deformed set of symmetry generators, which is a linear combination of the chiral density and the boson field, which is indeed still conserved even in the mid-IR theory. So at first, this might seem a bit confusing, right? Then why do I say the theory is anomalous? So from one perspective, you can say that I should just regard the n tilde theta, the conserved charge densities, as the correct charge densities and never worry about the chiral densities. However, the chiral densities are important, right? Because they are the gauge invariant densities, which correspond to the current operator. So if we just run the Noether procedure on the fermion action, we find that the electrical current is exactly proportional to some sum over these chiral densities. So the physical statement that we're making here is that the current operator is not exactly conserved, right? The current operator has an overlap with the conserved charge density, but it has an additional piece which is proportional to the boson field. And it's this additional piece that's proportional to the boson field that can potentially give rise to incoherent conductivity, as I mentioned in the preview of our results. Okay, so now we have a basic understanding of the symmetries and anomaly structure of this model, or really this family of models. We can begin to derive some transport results for the n=1 theory. So, as
maybe naive question.
go
Can
ahead,
you explain?
Yeah.
2 slides. I think you mentioned some term evolving this scalar field phi and also the form factor f over some Fermi velocity v. This term can be regarded as an internal gauge field. Can you say a few words? What kind of gauge field is one form? What gauge field is?
Oh, it's just so you can really, if you just stay within a single patch, right? In the single patch, the symmetry is U1, and the gauge field I'm turning on is just the is just the U1 gauge field. So this external U1 gauge field just gives you some electric field, which causes this chiral current flow in the 1+1D case. So here we have a similar story, but now instead of having an external gauge field, we have this internal fluctuating boson phi, which plays the role of it couples to the fermion in the same way as a U1 gauge field would couple to the fermions. So that therefore it will have the same anomaly equation.
And the usual space time index of the one form gauge field here will be some momentum index for the new internal gauge field you write down. Can you illuminate the index? Well, just what's the space-time analogous space-time index? I guess
the space-time index. Oh, sorry. Did you just mean that when I wrote a perp here, I didn't write the dependence on space-time?
Yeah, I didn't follow. What do you mean by the internal gauge field? What are the index, the space-time index, or maybe the momentum index? I just cannot see from this formula.
Oh, I see. Maybe that's the confusing part. So within the patch, you can choose a coordinate system, right? Where one direction is perpendicular to the Fermi surface. This is k-perp direction. And then you have the k-parallel direction. So here, the gauge field that we're turning on is really coupling to the current in the perpendicular direction.
Okay.
Right.
I think Ruben is asking about the Lorentz index of the gauge field.
The Lorentz index.
He's asking why it's the spatial component of the gauge field, and where the time component is.
Is this this one form gauge? And there's this is one form gauge field.
Yeah, but this is some external gauge field, so you can turn on whatever you want, right? So I turn on a gauge field which has a spatial component, which couples to this basically the perpendicular component of the current within a patch.
No, but the internal gauge field, is it a differential form? Is it a differential one form? Then you have an index, right? Maybe it's in momentum index, but I just didn't see the space-time or momentum space index. Maybe there's a AKX, AKY, AKZ, but
no. So that's.
I don't think there's an index. Yeah.
Maybe I should elaborate. So phi you should think of as the spatial component of a gauge field associated with this U1 symmetry in the patch. The temporal component, if you want, you could think of that as screened by the presence of the charge. So that's not really, it's not doing anything in the theory, and the reason why you can think of phi as being spatial component is just that you should think of it as coupling to the spatial current operator. That's it.
The point is that a gauge field in general will be some a mu, where mu is the space-time index, right? But here we've just coupling to a particular gauge field in which the time component is 0 and the component parallel to the Fermi surface is 0, and you only have a component perpendicular to the Fermi surface. It's just that the other components in this case can just be set to 0.
Okay, and that index is the space index or momentum space index?
Space index.
Space index. It's not a momentum gauge field. Momentum space gauge field.
It's not a gauge field in momentum space. It's just a regular gauge field in real space.
Okay, and that's dynamical, and that's a dynamical gauge field you should sum over in the path integral.
Exactly.
Yes.
Yeah.
Right.
Well, you sum over phi, but then the phi acts like a gauge field. So in effect, you're summing over the gauge field.
Yeah.
Thanks.
Yeah, I guess it's worth emphasizing that the dynamics of phi can in principle be different from a gauge field dynamics, right? The Landau action for phi that we wrote down is not constrained by gauge invariance, but this anomaly equation will hold independent of what dynamics we choose for phi.
Maybe a related question. So the next slide.
Next slide. Okay. Yeah.
Yes. Here, this n tilde is really gauge invariant.
Sorry, I didn't catch the. Here, the what is gauge invariant?
N tilde. The modified density.
Gauge invariant with respect to what?
I mean, there's.
Did you want to patch gauge symmetry or?
No. There's no dynamical gauge field here.
Right. There's no dynamical gauge field here.
Yeah. So if there is suppose we are talking about the dynamical U1 gauge field coupled to the Fermi surface, I can do similar things, but then the n tilde will not be gauge invariant. Here, this n tilde is gauge invariant, and it really represents some other concept quantity.
Yes.
Okay. Sorry, Gujin, I didn't quite follow what you were asking. I mean, the way we define it, our notation is such that the n tilde is always the gauge invariant thing.
If we are talking about the problem of the Fermi surface coupled to a dynamical U1 gauge field, then the analogous n tilde will be n plus something proportional to a, right?
Yeah, but the n is not gauge invariant, so it will work out such that the n tilde is the gauge invariant quantity.
I mean,
the notation in this slide
n is gauge invariant here.
N is gauge invariant and n tilde is not. Sorry, there's a long-running notational permutation between the members of this collaboration about the tildes on n's. But the gauge invariant n vis-a-vis the U1 in each particular patch is n and not n tilde here. And that's true in the manuscripts as well.
Okay, sorry, maybe I forgot the notation. But anyway, the point is that everything is consistent with, I mean, there's nothing different about a U1 gauge field compared with what we're saying here. That's what I point to make.
Yeah.
Hold on, let's make sure. So for U1 gauge field, n or asymptomatic, n is always gauge invariant. But for U1 gauge field, n tilde is not. For asymptomatic, n tilde is. Am I correct?
So I think, Liu, you're worried about how phi transforms under the gauge symmetry?
If it's asymptomatic, then there's no gauge transformation. There's no true gauge transformation.
Yes, that's right.
There is, it just couples to a different subgroup of that. You could think of the Fermi surface as being some product of, as having some product of U1s on each individual patch. And for the Ising-Nematic case, it couples to the current associated with some subgroup of that U1 to the n sub-patch symmetry. And for, like, say, an ordinary gauge field in the case of like a spin-on Fermi surface or something, it would couple to a different subgroup. But you can still think of Ising-Nematic as having a quote-unquote gauge symmetry under this large symmetry group.
Phi is not a gauge field, right? Phi is gauge invariant. So in the Ising-Nematic case, N tilde is also gauge invariant. Am I right?
So maybe it's a question of gauging under what? Like,
Yeah,
Right.
You can treat phi as being like a gauge field, and then it's then not gauge invariant under that gauge transformation, which is a different one from like the original global.
Yeah.
Maybe I'm talking about the more macroscopic gauge invariance, meaning whether this operator is a local operator at all.
Yeah, of course, the microscopic gauge invariance is only there if you're considering a gauge field problem, right? Whether it's asymptotic or loop current or anything, there's no microscopic gauge field. But I think perhaps the question is about the IR, this mid-IR theory. These order parameters couple in a way where you can think of them as coupling as the spatial component of a gauge field of some emergent symmetry. But that's not what you're talking about.
Can I rephrase it? I'm just asking, in the asymptotic case and in the U1 gauge field case, if I ask what are the conserved quantities and local conserved quantities, meaning gauge invariant measurable conserved quantities, are they the same or different?
I mean, there is no microscopic U1. There's no microscopic gauge field, right? So the operator phi itself is a measurable operator. It's just the order parameter.
Yeah.
And then everything in this equation is measurable in that case.
Yeah. But if it's U1 gauge field, then N tilde is not.
That's right. Yeah.
Yeah, that's what I want to say.
Yeah.
Yeah. Yeah. Thanks for raising that point. Okay, so if there are no other questions, let's go to the transport results for n equals 1 model. Yeah, so again, we start with this deformed set of.
Sorry.
Yeah.
Maybe let me just make sure, in the context of what you say about symmetry and anomaly in that slide, what's the symmetry here? Is it U1 or is it a loop group U1?
Yeah, so it's not quite a loop group, right? Because we discretize the Fermi surface into patches. So say we have the number of patches, say that is equal to n, then this U1 patch symmetry will roughly correspond to U1 to the n. So
yeah, but morally it's the loop group, right? It's just because we have discrete patches, when it's not quite there, but essentially, morally it's that.
So particularly, you can also show that the anomaly equation we derive, if you take this limit as n goes to infinity, you can recover the LU1 anomaly equations that Dominic, Ryan, and Senthil discussed in their previous papers.
Okay. Yes, I'm thinking something. Maybe I'll ask you later. Thanks.
Okay. Yeah. Thanks. Okay. So the deformed set of generators, right? This anomaly equation really gives us a relationship between the conserved charge and the chiral charge, and we know that the physical current operator, right, is given by a sum over different patches, right? Where you take the velocity, the Fermi velocity within each patch, and multiply it by the chiral density, not the conserved density. So now how do we get from this anomaly equation to transport? It really just requires two simple ideas. The first idea is, given that the n tilde charges are actually conserved, right? The time derivative of the current operator will be related to the time derivative of the internal sort of order parameter field phi via the anomaly equation. As a result, because the conductivity is a 2-point correlation function of the currents, we can relate the conductivity to a 2-point correlation function of the bosons, which will be simpler to determine. And the second idea is that if we combine the anomaly with the equation of motion for the boson, we'll actually be able to determine the boson correlation function at 0 momentum, but finite frequency. So we mentioned that, again, this is not in the quantum critical regime, right? The critical boson fluctuations will live in this different regime, omega much less than Q. But at least at Q equals 0, we can fix the boson 2-point function. And therefore, combining this with idea 1, fix the conductivity. So the concretes, the incarnation of these ideas in equation form will be the following. So the first idea.
Another quick, just previous slide. So let me just make sure again. So you are trying to, well, let's make an analogy to familiar like ABJ anomaly of U1. So there is some non-conservational current, usually chiral or actual current, and partial mu of J mu of the chiral current, maybe D star J 5. That's non-conserved. There are some terms on the right hand side. Usually there will be some terms like instanton density term like F wedge F. Maybe in 1+1 is the F term.
Yes.
But here some terms like modify that. So possibly something I'm asking whether that has some relation to some instanton density interpretations.
No, so if you do the gauge field case, then it's exactly the same as the 1+1D chiral anomaly in a particular choice of gauge, right?
Okay.
Yeah. So in the 1+1 case, your instanton density, what you're calling the instanton density is just a F01 component.
Yes.
Right?
Yes.
And this is in some gauge, this is just DDT of the spatial part of the vector potential, or DDT of A1. And in this particular example, the spatial component of the gauge field is just a component that's perpendicular in a direction perpendicular to the Fermi surface. And that's where, yeah, that's precisely the analogy.
Okay, but then the next thing is that the non-conservation of that current can be modified by modify that current to A some terms like Chen-Simons term. Let's say in 4D, 3+1D, then there's a term that you can modify the non-conserved star J, some of the current by adding some Chen-Simons like term. So I was wondering, say, whether the modification you have for N tilde is equal to M plus something else, whether that term has some terms also some Chen-Simons or quantum hole type of interpretation. Do you know?
Sorry, I don't. Maybe the others can comment on this. I don't really know.
You were asking the normal equation is just that the d mu d star mu is like F wedge F, right? So what Chen-Simons terms are you talking about here?
Like A wedge F. You can modify the current J as something like J tilde, and J tilde is J plus possible sometimes like A wedge F. But there is some issue about defining that. But my main point here is that there's if you try to consider symmetries invertible, there's some issue to define that current meaningful way. But if it's non-invertible, then there's some discrete U1 subgroup that's meaningful. I'm getting that part of the question, but I don't know whether. I'm just asking whether this has interpretation of Chen-Simons term or some.
Super.
Huh?
I think what you are talking about, the non-invertible stuff, applies specifically to 3+1D.
Oh, yeah.
Optical symmetry is a one-form symmetry. Here, you can also see the structure of the Chen-Simons. This phi is the analogous of A, which is the lower dimensional analog of Chen-Simons. 0+1D Chen-Simons.
Okay. Yeah, maybe just like some gauge field, right? The 0+1D Chen-Simons just some gauge field, yeah. Maybe little a. Okay. Right. Okay, fine. Okay, maybe we can discuss later, but thanks. Okay.
I see some raised hands, so maybe, yeah. Hank?
Yeah, so just a naive question. So what's the meaning of the Q equals 0 limits? Like, because you have a Fermi surface, so Q equals 0 is inside, right?
Sorry, I have a Fermi surface, so what?
You have a Fermi surface, right? Yeah, and Q equals 0 is inside the Fermi surface, right? So what kind of current is that? I'm just wondering.
Oh,
because yeah.
This Q, so we should think about this Q as a bosonic momentum, right? Not a fermionic momentum.
Oh, so for phi, okay.
Yeah. It's a for phi and for n theta. So right, n theta is a fermion bilinear. It's not a single fermion operator.
Okay, I see. Okay.
Yeah, it's just telling you that we are considering sort of spatially uniform source, which
Okay. Okay. Thank you.
yeah, this is the standard limit we take in transport calculations. Yeah. All right. So we have these two ideas, right? Now we want to translate these ideas into concrete equations. I won't go through the details, but basically idea one translates to an exact relationship between the conductivity and the the conductivity and the boson 2-point function, this DAB. So this DAB, you should think about it as the correlation function between phi A and phi B. This phi can have multiple components. So the first term, this Dij free, is just the free fermion Judo weight. So this comes from basically the diamagnetic part of the current. And then the second part is exactly the relationship I was talking about earlier, where we converted a calculation of the current 2-point function into a calculation of the boson 2-point function. So that was idea one. Now idea two is that we can actually use the boson equation of motion plus the anomaly to fix the self-energy for the boson. And the self-energy turns out to be a constant in the IR limit. So if we drop the irrelevant sort of bare interaction term, right, and we set the mass to 0, then we find that the self-energy determines the boson correlator at Q equals 0. So if we plug this constant boson correlator into idea one, we find a formula for the conductivity, which is, if you take the real part, it's really just a Juda peak with no other frequency-dependent correction. So let me emphasize that this is a fixed point result, right? It's a non-perturbative result in the mid-IR theory, which descends down to the fixed point. And it tells us that critical fluctuations cannot generate any incoherent fixed point conductivity, at least in this family of models. So as a bonus, using similar techniques, right, plus some path integral manipulations, we can also obtain some exact results for the susceptibilities between different operators in the IR theory. So these susceptibilities will be essential for the transport calculation in the random flavor model, although they won't be very important for the derivation we just showed. So these susceptibilities are very simple to state, right? They basically say that the chiral density and the boson field do not mix, right? This is manifested in the equation in the middle, that the mixed susceptibility between these two objects is 0. But the chiral densities themselves have some susceptibility, and the boson field also has some susceptibility. And it turns out the susceptibility of the boson is exactly proportional to 1 over mc squared, where this mc squared is the mass that appears in the mid-IR action for the boson. So this is telling you that there's no mass renormalization from the mid-IR theory down to the IR fixed point. This is a result that confirms a different argument by Malitsky and Sachdev from many years ago. So if we combine this with the anomaly equation, which gives you a relationship between n theta and n tilde theta, then we see that the conserved charge densities n tilde theta have a susceptibility amongst themselves, which is more complicated than just a delta function. Right? And this susceptibility in particular, it will diverge in the order parameter channel as 1 over mc squared. This again confirms various perturbative calculations that have appeared in the past. So yeah, as I said, this will be a bonus from the perspective of n equals 1 theory because we didn't really need it for transport, but these relations will play an essential role in the part to come. Okay, so now we come to the final part of the story where we determine optical transport in the random flavor larger model. So for notational convenience, we will refer to this as the RF model. And we want to ask ourselves, okay, we had some results for n equals 1, and which of these results actually extend beyond the n equals 1 family? Generally, the relationship between the current and the boson field will survive. Right? This is because the anomaly equation will always relate the current to some boson field. Juven, yes?
Yes. I just want to make sure, did you derive those results or you just claim the result?
Yeah, so I claimed the results and I gave you a rough idea of the intuition behind these results. But the detailed derivations are in our paper from April. Yeah, I want to focus on the derivation will be more complete in the random flavor model. Indeed. Yeah, here I just gave this is just an intuitive way to structure the conclusions.
Yes, okay, thanks.
Yeah, thanks. Yeah, so the n equals 1 model, we really had 3 types of results, right? We had a relationship between the conductivity and the boson correlation function. And this is a general result, which will continue to hold so long as your anomaly relates some fermion bilinear to some boson. The second equation, which contains, basically directly follows from path integral manipulations plus the anomaly equation, will also hold in a more general theory. However, the part of the conclusion that wouldn't hold is the exact statement that in the IR limit, the boson correlation function will approach a constant, which is independent of frequency. So this is the relation that will be violated in the random flavor larger model. And what we'll find instead is that indeed the boson self-energy will pick up some frequency dependence, and in turn this will generate some incoherent frequency dependent fixed point conductivity, which in the inversion-odd case gives us this omega to the minus 2 over z that we previewed in the beginning. Okay, so to get there, we have to introduce the random flavor model, and it's not really very different from the previous class, right? So here in the boson action, instead of having a single flavor, we'll have n flavors of bosons. Because there's no Owen symmetry, the mass matrix for the boson can in principle be arbitrary. Right? So we included this Mij, phi I, phi j coupling in the quadratic part of the boson action. And the interacting part of the action, as I said, will contain some Yukawa random GIJK couplings, which has this Gaussian statistics. So this model was first introduced. Yes?
For the uninitiated, why should I care about large n? Usually with large n stuff, I thought it's because we can't do small n, and then I go to large n because it gives me analytic control. But it seems like you just did it exactly for small n. Yes, exactly. So in the spirit of this talk is that we want to generate some model which has incoherent fixed point conductivity. And in n equals 1 model, exactly, we saw that there is no, the critical fluctuations cannot give you that conductivity. So that's why we want to consider a different model with a more complicated anomaly structure, which can potentially give you a frequency dependent conductivity. So you can say, okay, how physical is this model? We'll have more comments on that later when we, after we discuss our results. But essentially our conclusion will be that this model is not particularly physical. And it's, so you're right. We really need better models for which a natural frequency dependent conductivity emerges. Does that make sense? Okay. Yeah, thank you so much. Yeah, thanks, so. All right, so this model was first analyzed, right, in this particular incarnation, was first analyzed by Esterlis et al. In this in their paper from last year. And the key result is that if you do the disorder average over these GIJK couplings, the larger limit is exactly equivalent to the Migdal-Eliashberg theorem. So by that, I mean that the exact boson self-energy is just given by the one loop result, but where all the self-energy corrections in the fermion propagators are resummed. So here, the solid lines that I'm drawing really correspond to the full fermion propagators rather than the bare fermion propagators. And similarly, for the fermion self-energy, it's again given by a single one loop diagram with exact boson and exact fermion self propagators. So this is, you can't just go ahead and evaluate this in a diagrammatic expansion, right? This is really a set of self-consistent equations that you have to solve. But the solutions to these equations are very well known. And they basically reproduce the one loop singularities that I was discussing in the very beginning. So, okay, but here, following the philosophy of symmetries and anomalies in an n equals 1 model, we want to consider a mid-IR formulation of this random flavor model. And in the mid-IR formulation, again, the fermion dispersion, right, we'll introduce this dispersion perpendicular to the Fermi surface, a linear dispersion perpendicular to the Fermi surface, and quadratic dispersion parallel to the Fermi surface. And the interaction term will again be reduced to this sum over patches, where within each patch, we take the form factor to be independent of momentum. So also for notational convenience, we'll choose F to be a scalar here, so it doesn't carry any additional indices. Okay, so the symmetry structure of this action, right, will be different from the symmetry structure of the n equals 1 model. In particular, we note that the kinetic part, the fermion, the quadratic part of the fermion action will actually be invariant under a UN patch symmetry. So within each patch theta, you can do a UN rotation of the fermionic fields. And associated with this UN patch symmetry will be some UN conserved currents, right, which mix the different flavors of fermions. So now we can think about the UN analog of the anomaly equation, right? We can couple some external UN gauge field to this to the perpendicular current, and we find that there's an exact anomaly equation, which is very much similar to the one we derived before for the U1 anomaly equation. And again, in the coupling, so if we now look at the interaction term, the coupling of the boson to the fermions exactly mimics the coupling of this gauge field if we make the identification of Gij phi k summed over k with the non-abelian gauge field Aij. So given this identification and specifying to the sort of U1 patch subgroup, right? Because physically, right, the physical current is going to be the current summed over the different flavors of fermions. So the physical U1 patch current will be a trace of the non-abelian currents, and the trace of the non-abelian currents inherits the anomaly for the U1 subgroup, which is indeed given by a trace of the. So the right-hand side, instead of being the time derivative of the gauge field, it'll be the time derivative of the trace of the effective gauge field. So here, after taking a trace, we find the structure, which is sum over ik, Gij phi k. But morally speaking, really, the anomalies equation has the same structure as before. It's just telling us, it's just telling us that in theta, the chiral densities are not conserved, and the real conserved densities is a linear combination of n theta and some other linear combination of the bosonic fields phi k, which now have n different flavors. So using the exact same arguments as before, right? You do some path integral manipulations, you can derive the susceptibility for these chiral charge densities as well as the boson fields, even in this random flavor larger model. And we have the deformation of the U1 patch generator, exactly the same as before. And here, for convenience, we just introduce the capital GK so that we don't have to keep writing this GIK sum. Yeah, and the susceptibilities for the conserved charge U1 patch charge densities also follow from the susceptibilities of the chiral charge densities. So the only difference from the n equals 1 is that we have some extra indices, but they don't really change the essential structure. This is what we promised in the beginning of this section. Okay, so we said that these exact susceptibilities will be useful for transport. So how will they be useful? And the usefulness, before we get there, let me just comment on two conceptual observations, right? Two conceptual observations about the general structure of this large N theory, which will be useful to keep in mind. The first observation is that the critical point that we're accessing in this model is not really a simple critical point. It's a multi-critical point. So because criticality has to occur when all eigenvalues of the boson susceptibility matrix diverges, right? This is what defines the this is what we mean when we say that all the bosons have gone massless, right? But because for fixed choice of Gij, there is no inherent ON symmetry in the problem, we need to tune all n square entries of the Mij mass matrix in order to hit the multi-critical point. This is not the case for any of the other perturbative expansions that access the n equals 1 fixed point. And of course, we know that n equals 1 fixed point does not have these n square components. It just has a single mass matrix, and therefore that's just an ordinary quantum critical point. And the second conceptual observation we want to make is that for large n, there is actually a slow mode in the system. By slow mode, we mean that the relaxation rate of some modes in the system will actually scale as 1 over n, so that the relaxation rate goes to 0 as we take the n goes to infinity limit. And this is a serious problem for transport. Or, well, it's not a serious problem, but it causes some subtleties in transport calculations, because this means that taking the large n limit, in which case the relaxation rate goes to 0, doesn't commute with taking the IR limit. And the direct 1 over n expansion will break down actually in the ultimate IR fixed point. So a very simple signature of the breakdown is what we call a Judah weight mismatch, right? So the Judah weight can be extracted by multiplying your conductivity by omega, and then taking the omega goes to 0 limit before you take the n goes to infinity limit. But it turns out that because these two limits don't commute, right? If you take the two limits in the wrong order, you actually get an incorrect answer. And that answer is what you would obtain if you just did a direct 1/n expansion without worrying about the existence of the slow modes. So how do we resolve this issue, right? To actually understand transport in this model, we have to treat these slow modes properly. And the correct framework for treating these slow modes is the memory matrix formalism. Right? So the memory matrix formalism is has a very simple sort of algorithm to carry out. So the basic observation is that you can isolate, right? You can isolate the contribution to your conductivity from slow modes from the fast modes, because the slow modes and fast modes are very, very different, are on very, very different time scales. So basically for IR transport, you don't have to worry about the fast modes. And so within the slow subspace, you would have to identify, the set of operators that generate your slow subspace. And you have to compute this relaxation rate matrix, which tells you how fast an operator OI in the subspace relaxes with respect to some source, which is conjugate to OJ. So then we need to rotate to a basis which diagonalizes the relaxation rate matrix. So after we have this diagonalized form, then for every operator in this slow subspace, which overlaps with the current operator, we should expect some Judah-like response. Right? By Judah-like response, I really just mean you have some constant and you have this minus I omega plus some decay rate. Right? This is the simple-minded Judah formula, but it turns out that it will also hold. So the general conductivity we obtain will also be a sum of these Judah-like contributions, although the decay rates themselves will involve, in general, omega and t-dependent function, which can be calculated from the microscopic model. So in here, you can see that a slow mode can be easily treated, right? Because if we're calculating the relaxation rate matrix, then it's okay if there's a slow mode that scales as 1/n. We can just plug that slow mode into the denominator here and obtain the conductivity accordingly. But if we took the 1/n goes to infinity limit first, then the gamma A decay rate will just go to 0 in the n goes to infinity limit. And we would not see the effect that the slow mode has at any finite n. So, okay. So this is the general framework, right? We want to calculate a bunch of, the conductivity as a sum over different slow mode contributions. But here we have two very technical challenges. One challenge is how do we compute the static susceptibilities, right? In general, because we have a large number of operators in the slow subspace, we don't expect to be able to compute all of them. And the second problem is how do we compute and diagonalize the rate matrix to leading order in the 1/n expansion? So these two technical challenges will be tackled by what we call the anomaly-assisted large N expansion. So in the random flavor model, the slow subspace will really be generated, as we've seen, by these conserved charge densities on each patch and the boson fields that they couple to. So if we make that assumption, right, that these are the slow modes that we care about, then the general framework, right, of anomaly-assisted large N expansion is the following. So we take our ingredients, which is anomaly equations plus the large N expansion. The anomaly equations, as we have seen, give rise to some exact susceptibilities, which provides, which solves the first technical challenge that we presented on the previous slide. And a combination of anomaly equation and the large N expansion will turn out also to give us the relaxation rate matrix, at least to leading order in 1/n. So if we combine the relaxation rate matrix and the anomaly and the susceptibilities, we can plug them into the formula for the conductivity. And if we sum up the contribution from all these different slow modes, we will obtain our final formula. So what are these? Okay, Juven, yes.
You can. I have a question, but you say what are these? You can finish your sentence first.
Oh yeah. I was just saying. Now we're going to discuss these slow modes and their contributions to the conductivity.
Okay, great. So my question is that anomaly here, I suppose these are like a local anomaly captured by Feynman graph, right? These are the Z class anomaly. and there should be some quantized coefficient. So since you are using anomaly to govern possibly transpose and susceptibility type of things, what are the quantized coefficient show up in the calculation? Are there some discrete class, Z class or coefficient? Certainly it's not the flavor n there, right? There should be some other quantization, is it?
Yeah, so the quantized coefficient is really what occurs in the 1+1D analog, right? So here in the 2+1D example, we're not strictly talking about the chiral anomaly. We're thinking about the patch as a stack of chiral anomalies with some patch width, right? So of course, the chiral anomaly coefficient will be quantized. But once you multiply by the stack, then you have some prefactor, which is proportional to the width of your patch. So that width of the patch will, of course, not be quantized. And that's that will appear, for example, in the susceptibilities and will appear in the conductivity.
Yeah, but there is a quantized coefficient. It's just to compute the the quantized coefficient is multiplied by the patch width, as you said.
Yeah, exactly.
But I mean, there is a quantized coefficient that comes in front of that. I think that's what Driven is referring to, probably, right?
Yes, but patch width is just a theoretical construct, right? Like in the experiments, we don't know how many patches. So what are the outcome physical quantities that will be characterized? For example, the whole conductance, there will be a quantized plateau. Those are related to the coefficient on the 1+1D edge of this quantized coefficient for the anomaly index. And how about here? Are there some quantities? Maybe it's not quantized due to maybe the Fermi surface, whatever, but I just how do I see that? There is some quantization somewhere.
So just to be clear, the final results we get are independent of the patch width, because you have like some number of patches, and then the width is like, the width, the number of patches and the width of patches inversely proportional. So in the final results, everything will cancel out. So it doesn't depend on the patch width, but it does depend on like the shape of the Fermi surface and stuff like that. Yes.
But should there be some coefficient from, maybe you are dealing with maybe k equal to 1? Is there generically maybe other k or something? Maybe in certain cases, the flavor index may relate to this k coefficient of the anomaly.
In this particular model, at least, the flavor index is not related to the coefficient.
Yeah, it's generally not.
Was saying the coefficient is just 1, basically. After you
include it is related. The coefficient, the quantized coefficient of this anomaly is proportional to n in this model, which is the number of flavor indices. So in that sense, it is related.
Okay, that depends on how you scale, how you define your anyways.
Okay, so I suppose in general, possibly just be linear proportional to that anomaly coefficient. And right now you are dealing with the k equal to 1, I suppose. That's what I assume is the case.
Well, okay, at k equals n, I'm not sure I understood what Darius was saying about scaling. Like, there's only one definition of k here, I think.
I just mean that the time derivative of the chiral charge density will be basically proportional to trace of the ddt of the vector potential. Without, there's no prefactor of n once you take the trace, right? Like in the, I don't know. Yeah, I guess I'm talking about this equation. So in the last line of this equation, if you absorb this sum over ik GIIK over n phi k, that's what we define as this effective gauge field. Then this anomaly equation on the right hand side is really just the patch width times some time derivative of the trace of the gauge field with no extra factor of n in front.
Yeah, okay, but if you think about specifically a U1 gauge field, I was thinking of you're thinking about the current as being a UN current. I was thinking just U1 current. So there's a factor of n between those. Okay, I see what you're saying. But like just for the U1 symmetry, the anomaly coefficient is proportional to n.
Yeah.
Yeah, so driven, I mean, the only interpretation I have of the anomaly coefficient, like not just in this model, but just in general for this idea of a root group anomaly, is that it's basically the number of components of the fermion. Like for example, spinful fermion, it would have anomaly coefficient equal to 2. Here you have an n component fermion, so it's anomaly coefficient is n.
Yeah. Anyway, I think I know the answer. At least a rough answer. Thanks.
Okay. Yeah. Thanks, Dominic, for helping out. All right. So here I presented the general sort of workflow for calculating the conductivity. And now let's just discuss the different slow modes that appear and how they contribute to the conductivity. Right. So the dimension of our slow subspace will be number of patches plus the number of flavors, right? Because the subspace is generated by these n tilde thetas and the phi i's. So there's a subspace of dimension and patch, which is just generated by the conserved operators n tilde theta. And we know that because these are conserved operators, the relaxation rate is exactly 0. As a result, we get a coherent Juda peak, which is what we advertised in the beginning of the talk. And then there's a single mode, which is this particular linear combination of the phi field, this sum over I, gi, phi I, which we know from the anomaly equation, right? This is the mode which deforms the conservation law of n theta. And this mode has a relaxation rate, which scales as 1 over n times some function of omega over t, which is order 1. So this is a sense in which we have a slow decay rate, right? This gamma is proportional to 1 over n. And this will, in fact, lead to the incoherent critical conductivity, which we'll discuss in the next slide. And the remaining n-1 modes will be the orthogonal other linear combinations of the phi I fields, which are orthogonal to this sum over I, gi, phi I. And these modes will have 0 decay rate, which suggests that they should give you an additional Juda peak, but actually because they don't have any overlap with the current operator, because they don't have any overlap with the current operator, that actually do not contribute to the conductivity. So from this analysis of slow modes, we have a very clear decomposition of the coherent and incoherent conductivities that enter this model. And that brings us to our final results in the anomaly-assisted approach. The coherent Juda peak is exactly the same as in the n = 1 example, except for this overall factor of n in front. But the incoherent conductivity will have a more interesting form, right? If we just copy-paste the Juda formula, in the denominator, we have this omega plus I times the decay rate. And the decay rate is given by, in the previous slide, I wasn't very specific about this order 1 function in the decay rate. But here, it's really an inverse times the what's called the memory matrix between phi I and phi j fields. So for the purpose of this talk, we won't talk about exactly what this memory matrix means, but you can see this is proportional to the decay rate. And the point is that via a series of exact Green's function manipulations, we're actually able to calculate this memory matrix within this large and random flavor theory. So the final result we find is that this particular combination of the memory matrix components is given by I omega times the inverse of the Largen solution to the boson self-energy, which followed from Ilya-Ashberg theory, as has been shown in the original works of Esterles et al. So now if we plug this part of the memory matrix back into the decay rate, into the incoherent decay rate gamma, we'll get a final formula, which is gamma equal to omega over n times the number of constants and times the inverse boson self-energy. So in the final step, we just evaluate the boson self-energy, right? This is a standard calculation in Migdal-Ilya-Ashberg theory. We combine it with the formula on the previous page, and we obtain the final scaling for the conductivity, which, in the regime where omega is much larger than t, we recover this omega to the -2 over z result that we quoted in the beginning. But in the regime where the T is much greater than omega, actually, it turns out that thermal effects begin to dominate over quantum effects. And we have this 1 over square root of T scaling, which is has different power from the omega to the minus 2 over Z in the 0 temperature limit. So this is our final result. And there are a few remarks to be made about this result. First of all, we note that for inversion even order parameters, the incoherent conductivity actually vanishes, right? This is because these trace thetas, which are effectively summing over the entire Fermi surface. So for example, trace theta of VF theta times F theta, because in the inversion even case, F doesn't change sign as we go from plus K to minus K, but the Fermi velocity changes sign from plus K to minus K. So when we sum over all the patches, the coefficient of this incoherent conductivity actually vanishes in the case of inversion even order parameters. And we do not get critical incoherent conductivity. However, in the inversion odd case, VF and F have the same symmetries. Therefore, the coefficient is non-zero, and we indeed find a non-trivial incoherent conductivity. And we again emphasize that the non-perturbative anomalies and symmetries are indeed essential, because this result is beyond a direct 1 over n expansion, which would have missed both the incoherent piece and the second term in the coherent piece. In other words, if you did a direct 1 over n expansion, you would have found that the conductivity is just given by the free fermion Juda weight, which is incorrect. And finally, as we commented on earlier, because quantum effects dominate over thermal effects at finite temperature, this does not fulfill our goal of achieving sort of omega over T scaling in the incoherent part of the conductivity. And as a final remark, let's remind ourselves, right, why we're able to get this result in the large N theory, which is different from the n equals 1 theory, despite the fact that we have this similar relationship between the conductivity and the boson correlation function. And the key point is that in the n equals 1 theory, as we said, the boson self-energy is really just a constant for Q equals 0 in the IR limit. This combined with the fact that the boson correlation function is directly related to the conductivity tells us immediately that the conductivity will also just be a pure Juda peak with no incoherent correction in the n equals 1 theory. However, as we have seen, in the random flavor model, the dynamics is different. And the dynamics generates a frequency-dependent boson self-energy. And this frequency dependence is exactly what led to the critical conductivity that we commented on. Okay, so that brings us to our last slide. We started with the motivating question: can we find a clean model of non-Fermi liquid that exhibits quantum critical transport in the IR limit? And in this talk, we provided concrete answers to this question. And the answer is no for standard n equals 1 Hertz-Millis models. This family actually includes various perturbative expansions, including the standard RPA expansion, the small z-2 expansion, and also the matrix large N expansion. However, we found that the answer is a quasi-yes for random flavor models, at least with inversion-odd order parameter. And by quasi-yes, I mean that although the T equals 0 conductivity is sensitive to the critical exponents of the theory, at finite temperature, some dangerously irrelevant operators turn on and the thermal effects start to dominate over the quantum effects. So we don't have quantum critical scaling. The key point we want to emphasize is really, these models are supposed to be toy models, right? They won't describe real systems. But the point of our novel methodology, which we dubbed anomaly-assisted large N expansion, is to build muscle for more realistic models, and likely more complicated models of non-Fermi liquids to be discovered in the future. So our hope is that these non-perturbative anomalies will extend beyond this Hertz-Millis paradigm and allow us to sort of go beyond conventional perturbation theory in these calculations in more complicated models. So as a final point to make, we note that along the way, we found the random flavor model, although it's an interesting theory on its own, which has a frequency-dependent incoherent conductivity, has a number of peculiarities, one of them being the multi-criticality, the n-squared relevant mass operators, and the other being the unusual anomaly structure, which is essentially distinct from the n=1 model. So that tells us that there's really a need to find better physical models. And well, we already have enough reasons to think that Hertz-Millis is not enough, but this just adds to, it adds an additional motivation for us to search beyond Hertz-Millis criticality in the context of non-Fermi liquid models. And here I just list a number of open questions. And with that, thanks for your attention and thanks for all the great questions. Yeah, I can take more questions, but.
Okay, thank you. Thank you, Zhengyan. Thank you, Zhengyan, and thanks. Question from the audience. Let me see. So please go ahead.
Yeah, thank you for the talk. It was very clear. So I had a question. So in the very beginning, you showed that there was 3 different energy scales. There's the UV, the mid-IR, and the IR. I was just wondering if you could summarize at these 3 different energy scales what the symmetries were and what whether these symmetries were anomalous. Thank you.
Yeah, great. So at the UV scale, right? The UV scale, the symmetry is really, well, actually, in a deep UV, you should think that your model always just have some lattice translation symmetry and a U1 symmetry, right? And these are not anomalous. But once we go to the mid-IR theory, the symmetry became this U1 patch symmetry, right? And the chiral densities in the U1 patch theory are indeed anomalous. And this U1 patch symmetry in the deep IR limit then will become this LU1 symmetry, which is the loop group, right? Because the patch, instead of considering the total charge within each patch, in the LU1 symmetry, the generators will become the charge densities for different points on the Fermi surface. And again,
okay.
These IR symmetries will be anomalous indeed.
Yeah, okay. So you start off with, so all of these anomalies are anomalies of symmetries which are emergent. Is that right?
Indeed.
Okay, thank you.
Well, I should mention that so we are going for dinner with Darius, maybe sometime after 5:30, and there are so far 4 people to join. So if you have interest to join us, please send me an email. It should be free. So any more questions from the audience?
Can you say more about the BCS?
Well, that's a great question, Liu, but this is partly from the recent works from Sunsik's group, right, where they were investigating the spin density wave case, which is of course different from this Q=0 criticality that we're considering here. But the interesting thing they were finding there is that if you just consider, right, in the absence of BCS coupling, the critical theory there is just well described by the by a finite number of hotspots on the Fermi surface. But what they found is that in the presence of BCS couplings, large angle scatterings might start to play an important role. Right, the BCS coupling strength between distant patches will decay as some power of the distance and momentum space between these patches. And if this decay is not fast enough, then you cannot neglect the interpatch scatterings. And this is the sense in which I mean the validity of the patch theory in the presence of BCS couplings needs to be scrutinized more in the future. But obviously, I didn't do this work. So because Sunsik is at perimeter, maybe it'll be good to talk to.
Lujin, the person asking the question, I think is involved in this.
Oh,
in case you haven't met Lujin.
No, in the Borges at all. I thought
no, so, but yeah. Anyway.
Okay.
Lujin,
anyways, yes.
Maybe let me just ask about the BCS effect for Dominic's previous work on the loop U1. So if we consider spinel Fermi surface using Max's result for Cooper pairing, there will still be some finite BCS coupling strength at the fixed point. So how does this reconcile with the loop U1?
Well, it at least preserves a subgroup of the loop U1, right? We never really claim in the paper that you have to have a whole loop U1. You at least have to have an infinite dimensional group, but it could be a subgroup of OU1. I guess that's what happens when you have a finite BCS coupling.
I wonder if the following observation is important. At least in Max's result, the BCS coupling strengths in all angular momentum channels are the same. It means in momentum space, that kind of BCS coupling is still a delta function in momentum space, meaning it couples fermions just at the same point of the momentum. Maybe, I don't know if this means the loop U1 or the exact or the emergent conservation of each patch is still valid.
Well, the BCS coupling always involves Cooper pairs, so you always at least have scattering. You always at least be able to create electrons in pairs on antipodal patches, right?
But there are many angular momentum channels of the BCS coupling, and Max's result is that the fixed point values of all these angular momentum channels are the same. In momentum space, the angular momentum channels after Fourier transformation, in momentum space, it means the BCS coupling as a coupling function of momentum will be a delta function, meaning it will just scatter a pair of Cooper pairs at the same patch. I'm asking whether this interpretation helps to, whether it supports the existence of the loop U1.
Yeah, maybe if what you described it holds and still have a loop U1, but a more generic BCS coupling still preserves a subgroup of the loop U1. So maybe that's enough. Maybe the property you're describing will let you have a full loop U1.
I see.
But even with a subgroup, you can still recover many of the arguments that we're making. In fact, in the case of the spin-on Fermi surface, like what you're describing, so the sort of strict U1 gauge field, the arguments are exactly the same, given the particular subgroup that you get.
By particular subgroup, you mean the symmetry considered in this talk?
So I mean, in this talk, there's an assumption that you have the full symmetry. So Darius was not really talking about BCS, but by subgroup, I mean, in that particular case, you preserve the essentially axial rotations on antipodal patches, rather than the generic U1 on each individual patch. But that's enough to make all of the arguments that we're making here for the case of the spin-on Fermi surface.
Okay, thanks. Maybe I can ask later. Thanks.
Yeah, we're always happy to chat.
Thanks.
Maybe you can join us for dinner.
I'm in China.
Okay. I have a question relating to Liu Jun's question. The Fermi surface anomaly, I suppose for the Fermi liquid cases, in 2 plus 1D is described by something like a momentum space gauge field ADA, maybe AXDA, AXDX, which is the pure U1 anomaly or loop U1. And I'm not sure I get a message here for the non-Fermi liquid case. What are the form of the anomalies? Are there some terms you write down in 5 dimensions as 5-dimensional topological terms and capture the 2 plus 1D non-Fermi liquid anomaly?
Yeah, so I guess there is a way to think about our anomaly equation from that loop group. So first, I should emphasize that in the mid-IR theory, we don't have the loop group symmetry, right? So we're not thinking about we just have this U1 patch symmetry. right? But if you want to think about the full loop group symmetry, here's a heuristic way to think about it. So basically, in that 4+1 dimensional, so you're saying that this anomaly should descend from some 4+1 dimensional Chern-Simons term, right? And then the violation of current conservation in that case on the right-hand side will involve basically something like dA wedge dA. And in this dA wedge dA, one particular component will be ddt of some spatial component of AI, and then times dd theta of some other component of A, right? So A now has 4 different components, right? So this ddt of the spatial component of AI is exactly this ddt of phi that appears on the right-hand side. And the dd theta of this other component, A theta component of the gauge field, corresponds to this lambda of theta prefactor that appears here. So when you take the continuum limit, this lambda theta, effectively it becomes this partial theta of the Fermi momentum times the width of the patch in angular space. So yeah, if you take your charge densities so on the left-hand side, instead of taking full charges, you take charge densities, then on the right-hand side, this lambda theta will exactly become the partial theta of k theta.
So what's the 4+1D term look like? Is that A dt partial t phi and
yeah, maybe it's better if I just try to write it on the so instead of the equation here, what you would have on the right hand side would be something like right. So as we said, we identify this phi as some spatial components of the gauge field, right? And then this will be like a d theta of some other component of the gauge field. And these together, right, you can see how this appears in the anomaly equation, which is just dA wedge dA. Does that make sense?
Okay. And the phi d term will require another A.
No, the phi d term is the phi d Chern-Simons term, but the violation of current conservation is the 4D.
Yes.
So it's dA wedge dA, right? It's the same. It's the same thing that appears. Actually, it's probably not. Yeah, it's the same thing that appears in the chiral anomaly in 3+1 dimensions.
So this is still pure U1 anomaly. In
this 5D language, it's the LU1 anomaly. It's the LU1 anomaly of the 2+1 dimensional theory, but it will be the U1 anomaly associated with. You have to include the gauge field in the theta direction.
And there's no gravitational contribution. Is it correct? Even for both Fermi liquid and non-Fermi liquid. In 4+1, there's a U1, not just U1 cube anomaly. There's a U1 gravity anomaly, and that term does not contribute.
We never really thought about whether there's a gravitational contribution or not. I mean, that would be an interesting thing to think about.
But so far, is there any example with gravitational contribution or no? Or is there a no-go or what? I just want to make sure.
We haven't really addressed that either way, I think, I would say. We only focused on the gauge anomaly.
Okay, thanks. Okay, thank you very much. Any other question, comments? I think we have running over time a lot, but it's great to have some more discussion. Okay, thank you. Let's thanks Darius again.
Yeah.
And we will meet for dinner. If people still have interest, please send me an email. Thank you. Bye-bye.
Thanks.